Hi everyone, my name is Daniel, and today I'll be presenting our project on deep recurrent model for readmission and urgent care. Just a quick intro. The problem statement is below. So there are two groups of ICU patients that may strongly benefit from extending their stay at the ICU. One is patients that must be readmitted to the ICU, and two is deceased patients within 30 days of their first discharge. The objective is to predict if a patient is to be discharged by using chart events and demographic features. We believe that a hybrid deep learning model can outperform more traditional methods such as logistic regression. This is the same hypothesis in the original paper. Below, you can see a diagram of how our data is set up for prediction. First group is when users are in the ICU. They first discharge, and then we make predictions based off of their last 48 hours of chart events and demographics. Using this prediction, we can understand if a user is likely to be readmitted or result in death. Next, I'll go over the methodology. For this analysis, we used MIMIC data, which consists of data collected from over 40,000 patients of the Beth Israel Deaconess Medical Center's critical care units between 2001 and 2012. This data consists of 26 different tables, which captures a lot of information such as admission records, diagnoses, lab results, vital readings, demographic information, as well as doctor's notes. So for feature selection, first we will look at the chart events. We extracted the last 48 hours of ICU chart events. So this includes features such as blood pressure, heart rate, glucose, pH, body temperature. Similar to the paper, we also regress the chart events to determine statistics that we can use for logistic regression. So we looked at regressing the chart events over time so we can understand the rate of change and the base level for these chart events for each ICU visit. For the demographics, we use the following as features, so age, race, and sex. Date of birth for patients over 89 are shifted to comply with HIPAA regulation. As you can see, our age is slightly skewed to older groups. You do see there is some mass at the lowest group, potentially due to newborns or children. Next, I'll be going over the model architecture. So our computational implementation is here. For our project, we use the Google Colab environment. As you can see, we were able to partially replicate the environment. However, given our memory constraints, we did use Dask in the initial phases of pre-processing. Here you can see the model architecture. So this is the final model in which we compare to logistic regression and LTSM. First, we use 3 stacked bidirectional LSTM layers with TANH activation and dropout. This output is fed into 3 parallel CNN layers. Each layer has a single 1D filter, ReLU activation, 1D maxpol layer. The output of the 3 CNN layers are concatenated and fed into a fully connected layer. The charts on the left are from the original paper. The charts on the right are from our project. As you can see, the data is relatively imbalanced. Because of this, we propose an under and over sampling technique to rebalance the data. This allows us to make better predictions with less imbalance. So in this part, we tune the parameters of our model, and we use weights and biases to track these results. In this figure, you can see that the validation loss and accuracy will vary as we alter these parameters. For the specified ranges, it can be seen that higher learning rates and smaller batch sizes are giving better results, while hidden layer for LSTM is better if it's in the mid-range. Finally, you can see on the right, this is our final parameters for our models. Next, we validate our models. using the validation set, we can see that the validation loss plateaus, suggesting that further training may result in overfitting. On the right-hand side, you can see that our model's performance in the confusion matrix. The model's performance in the test dataset is consistent with the validation results, which shows that the model generalizes properly. Our results here support the hypothesis given from the paper that the LSTM plus CNN model outperforms other predictive models. As you can see, we use logistic regression here as a baseline as well as compared to LSTM. Although our metrics do differ in terms of absolute values from the original paper, we do hold the same hypothesis. So in each case, the logistic regression has the smallest AUC. In our LSTM model, it's the second highest, and then our LSTM plus CNN model has the best metrics overall. One thing that is interesting is that in our model, our recall is smaller in our LSTM plus CNN model compared to the LSTM model. However, when we look at the overall metrics, the LSTM plus CNN model is still performing the best. So just to conclude, we believe that the main constraints with reproducibility was with the ETL process and model tuning, but in the end, we were able to support the main hypothesis of the paper that utilizing an LSTM plus CNN model would outperform other models. You can see here that our our ROC and AUC curves are similar. So just to summarize, we believe that using chart events and demographics can make very strong predictions on whether or not a patient will be readmitted to the ICU. By further exploring these models and this analysis, this could be a good recommendation given to ICU doctors on whether or not a user should or should not be released from the hospital. Thank you.